of y. That's precisely the statement of this lemma. So what is happening here, for every x in this set here, we are getting exactly one y for which this is true, px comma y is true. That means this px comma y satisfies the vertical line test, and this is happening because of lemma 2 to 10. You can go back and see that this is the statement, and that's why this p can be used to define a function. Okay, and that function can be called a decrement function, because what it does is this: if you are giving this input, say your input is 2, then h of 2 will be that element whose successor is 2, and clearly that is 1, because 1 plus plus is equal to 2, y plus plus is equal to x. If you take x equal to 1, then this will be 0. So it gives you the previous number. That's why it decrements. However, h of 0 cannot be actually it need not be defined, because now 0 is not a part of the domain. That's why we have removed 0 from the domain, and we get a legitimate decrement function. That's how we get a legitimate decrement function h. In bracket we can write h of 0 need not be defined or is undefined. Because 0 is not in this set. Okay, so this is our first example. Now after this, there is another example which is, however, informal, because it uses real numbers with which we are not familiar yet. I mean, we are familiar, but we haven't seen it being presented formally. Okay, so anyway, let's just see the example. So this will be example 333, and this is informal. This example is informal because it uses real numbers which we will develop in only in chapter 5. Right now we are in the 3rd chapter. So here we will see all the basic things of axiomatic set theory. Although there will be some other things also which we will discuss in chapter 8, namely infinite sets, axiom of choice. So the basic things of axiomatic set theory we will see in this 3rd chapter. In 4th chapter we will develop the system of integers and the system of rational numbers. In the 5th chapter we will develop the system of real numbers. So until then we don't really know about real numbers. That's why these examples are being termed as informal. Okay. we may try to define a function k from the set of real numbers to the same set by using the property px comma y for here, since x and capital X and y are the same set, so our elements will be coming from that only. And this is my definition of the property. Y square is equal to x. Okay, so this is my property. But this property creates more problem than what we have had here. Unfortunately, P cannot be used to create a legitimate function k because of two problems. There are two difficulties here. The first is this. There are some x in R for which no real number y satisfies p x comma y. Okay, let me refill this. Okay, I need ink. So for some real numbers, x will not give you any y. That is one problem. And you probably can guess what those real numbers are. They are the negative real numbers. Because what we want here, we want x to be the square of some real numbers. But negative real numbers are not squares of any real number. That is the problem. That is one of the problems that prevents this property from creating a function. Okay, satisfies this. For example, when x is equal to -1, there is no real number y for which y square is equal to -1. That means p -1 comma y is not true for any real number y. This problem clearly can be solved since we are taking x from the domain, right? And the negative numbers are creating a problem here. So you remove the negative numbers, just like how we removed the 0 there, which was creating a problem in the previous example. So this can be solved by restricting R to the right half of the x-axis along with 0, of course, because 0 does not create a problem. If you want, you can remove 0, but there is no point in doing that. Okay. But even if you do that, in place of R, if you now have this closed ray, we may call it a closed ray. Why we call it a closed ray? We will see those things later on. So even if we do this, still there is a problem. That is the second problem. But even then, we will face this problem. For us, there is no negative value of x. We will choose x to be positive. So let us choose x equal to 4. There are two real numbers. Y equal to -2 and y is equal to 2, such that y square is equal to x. So the particle test is still failing. It's because for a given x we don't have a unique y for which this property is true. That will be true only when x is equal to 0. For every non-zero x, there will be a set of two y values for which this relation is true. Relation is going to be true. So here also we have to change the range to say remove the negative values so that we have only a unique y for a given x. Oh, I haven't said restricting what, right? Restricting the domain. Domain R, we are changing this one. Now this can be solved, the second problem, by restricting the range R again to 0, plus infinity. So now for x equal to 4, this choice is not present anymore. We only have y equal to 2. Once this is done, we have a legitimate function it has a symbol also. You already know what this function is. It's the square root function. Legitimate function, the square root function which for any x in the domain produces a unique root x. Again, this is a number, okay? This is a non-negative real number such that the square of root x is x. So this is our square root function, or we can call it a non-negative square root function. If instead of changing the range from R to this, if we choose to consider the negative real numbers, then we get the negative square root function. That is also a function, a different function. Okay, so now next we come to a very important point about the definition of a function that we have given. We sometimes specify a function by specifying its domain, say x, its range y, and how it generates the output fx from any given input x in x. That is, there is a formula that involves x, okay, that involves only x, and it tells you what this fx is. This is generally the way we specify functions. For example, we can write something like this: f from, I am again using real numbers, where you say what the output is explicitly. Say this is equal to x square. For a given x, the output is x square. You have to take the square of x. So when we specify a function like this, then we are saying how we are generating the output from the given input x explicitly. So what we have written here, and how it generates the output fx from a given input x. This is called an explicit definition of a function. In example 332, that is our first example, the increment function we gave it a name also. Anyway, it does not matter, because we are saying f here again. The increment function has an explicit definition. That is, it has been defined explicitly. For a given x, we are saying what the output is. Explicitly, we are saying how to generate the output. As opposed to this, on the other hand, if we there is another way of specifying a function. If we specify a function by specifying its domain x, domain and range must be specified, without which the function has no meaning. A domain x, a range y, and the relation px comma y that every output y for a, not every output, the output y for any given input must satisfy. Okay, so in the second way of specifying a function, we will specify, of course, the domain x, the range y, and the relation px comma y, which is defining the function. That is, we have to specify this relation that the output for a given input must satisfy. Okay, note the difference between these two things. Here the output fx is being generated from x, and we are saying exactly how the output is being generated. Here, however, we are not saying how y is being generated from x. We are just simply saying that for a given x, there is some y which is unique. Okay, that thing should be there. P must satisfy the vertical line test. For any given x, y should be unique. So in that way, y is being defined implicitly by this relation. So then we have an implicit definition. Okay, so what is the sentence? On the other hand, if we specify a function by specifying its domain and range and relation, so that this happens, then we have an implicit definition. For example, in the previous example 333, the square root function has an implicit definition, or has been defined implicitly by the relation y square is equal to x. Note that here for a given x, we are not saying what the output y is, or how it is being generated by x. More specifically, we are not saying y is equal to something. Of course, we are writing y is equal to root x, but that is just a symbol. It's not saying anything more than the fact that this is an element whose square is x. So here we are using the relation to define y from a given x, but implicitly. So in short, explicit definition looks like this. Y is equal to an expression involving x and an implicit definition looks like this: P of x comma y, which is a statement involving x and y from which we are not, we can't solve for y in terms of x, if that makes sense. Okay, so this is the difference between an implicit and explicit definition of a function, and this is important. Okay, now in both these ways of specifying a function, we are saying that we have to specify the domain and range. However, often we do not do that. Okay, for the sake of brevity or for making things short, say for example, we are working with only one function where we have already specified the domain and range somewhere, and we are having instances where we have to mention the function again and again. Then we will not write domain and range every time. So that's why sometimes we don't mention the domain and range of a function. For example, the increment function this is the full specification of the increment function, right? Where the definition is explicit, we are saying how fx is being generated from x. Also, we are specifying the domain and the range. But this, we abbreviate this sometimes like this. Or should I write sometimes specified? By writing the increment function fx equal to x plus plus. The domain and range are the set of natural numbers that is understood here, or fx equal to x plus plus, or x plus plus, or even the extremely short plus plus. It just denotes the function itself. For example, the ordinary addition operation, that can also be thought of as a function, but we use it on, I mean, we denote the function using only this symbol, although at this point I cannot tell you, or I can tell you actually. You see, if we think of the addition, this is the increment, right? After defining the increment, in the system of natural numbers, we define the addition. So if you think of that addition function, it can be defined as a function which looks like this. Actually, it's a function that looks like this, where this is the sum of the natural numbers m and n, but we denote this output by this symbol. Okay, and as such, this is nothing but m plus n. As such, instead of saying that addition is this function f, we sometimes say that addition is this function plus. So in that sense, we are using this symbol here. Although sometimes this may cause problem and confusion. Too much abbreviation can sometimes cause confusion.